Sorry, I didn't understand. You wanted me to start, or? Yeah, sure. Okay, I'll start. Yeah, thanks for the invite. Yeah, I'm also happy always to talk to people from TIFR. It's like my second home. Uh,
Is it still second home or third?
it's it's my second home. My first home is in Pilani, and second home is still in Mumbai.
I see. Great.
I miss the food, man. So it's still much better than Barcelona in terms of food.
Good.
Okay, so I don't know how many of you have read the abstract, but so today my idea was to talk a bit about the electro-absorption modulators I was working on in the half of my PhD, and so Subhajit asked me to make this talk a bit more heavy on introduction, so that everyone is on the same page, basically. And so I tried my best, but in any case, if you have any question, just feel free to stop me. It's also a good practice for me, so don't hesitate to ask questions. The more you ask, the better it is. But it should be clear to everyone, the at least the motivation. So I start with this title slide, and so this is an artistic image. One of my dear friend, David Alcaraz, he made it for me. So you could see there is the white thing is like the silicon waveguide, and then there is a 2D material flake on it, and you can ideally modulate the light based on the interaction with graphene. So, well, Subhajit already introduced me, but just to give a brief intro. So, most of my work in TIFR, I was in Mandar's group. So, I did my master's thesis with him, and then he kindly agreed for me to uh, so that I can stay one more year as a JRF. So we had I see lots of familiar faces in the audience today, like Vishwas, Surajit, Pratap, Subhajit. So like yeah, so I've been where you are right now, and it's a very good place to be. And now basically, so I'm a PhD student in quantum nano optoelectronics group headed by Frank Coppens. So, so ICFO is a very small research institute. So it's very much like TIFR. I would say a very similar environment. The only thing is ICFO is even smaller than TIFR, I think. But there are only PhD students and postdocs, and very small population, like 600, 700 people, I guess. And it's located in a very beautiful uh, town. It's called Castelldefels. It's like 10 kilometers from the main central Barcelona, but it's in the same province, and it's very beautiful. So if you get a chance to visit for a conference or anything, don't think twice. It's a very good place to be. Okay, so to begin with, I don't know how many of you have iPhones in your pocket, but so I just wanted to ask a very simple question. So Can you guess how many transistors the latest generation of iPhone have? So let's say iPhone 12. I already wrote it in my abstract, so and any guesses? No? Okay. Anyway, so well, iPhone 12 have almost 11.8 billion transistors, and thanks to this number, you can actually do 11 trillion operations per second. So that's like really, really fast. But what happens is when you stack 11 billion transistors so close to each other, they are so tightly packed near to each other that they suffer from losses. They talk to each other, so there are crosstalk issues. And right now, the technology is basically copper-based or aluminum-based interconnects. So that results in huge power consumption, and it eventually heats up your device. So what's the solution basically? Well, so if you want to go even faster than iPhone 12, for now we have to either stack even more closer these transistors, which would eventually be again, it would be more problematic, or we find a complete new the technology. So in all the conferences I've given a similar talk, I've always started with this stupid joke. So for some reason, nobody appreciated it, but I still like to do it. So it's basically, I took inspiration from these Marvel superheroes, Flash. So Flash was a normal person until lightning struck him one day, and it made him the fastest man alive. And I looked for resemblance with my project, and then I realized that if we take today's communication, and if we just shine light on it, it makes it a faster communication. So the idea is to you take your existing electrical communication systems like our phones, laptops, and we integrate it somehow with light. So the communication happens with photons instead of electrons, because photons are much faster than light and they are very, very less lossy. So to make an optical communication, now you basically, so let's say we want to communicate from Alice to Bob. So Alice would have an electrical signal generated from her device. Basically, could be a smartphone, could be a laptop, could be anything. And now this electrical signal needs to be converted into an optical signal, and then it goes through some guiding medium. And then this optical signal needs to convert back to electrical signal to reach to Bob. Now, there are tons of already very stable technologies in terms of guiding medium. So I'm sure you have heard about these optical fibers. Even there are these fiber internet connections already available in India, which are very good. And there are new technologies these days based on waveguides as well. So these are called optical waveguides, and you can engineer your dielectric environment such that the light only travels in a specific mode and only inside this optical waveguide without having any losses. But what's still the bottleneck in whole this chain is these interconnects where I put question marks. So you need to convert your electrical signal to an optical signal. So this needs to so this is still a bottleneck. There are not a lot of interconnects available right now to do so efficiently, and the same goes for the reverse, from the optical signal to an electrical signal. So what you need is basically a photodetector, which converts a light signal to an electrical signal, and you need a modulator, which converts an electrical signal to a light signal. And both of these interconnects are called optical interconnects. So far there have been a lot of research in this domain from many years. I think more than 10 years. So a lot of people are trying to move to optics, also in also with silicon, because it's already CMOS compatible, and hence provides a huge advantage in terms of manufacturing capabilities. So there have been lots of attempts with different technologies. So one of the most common one is these silicon-based Mach-Zehnder interferometers. So, but the problem is that in silicon, in order to change even a tiny bit of absorption, you need huge surface area. So at the end, you need two large devices, which results in increasing the footprint of the device. And hence, they are not very promising in terms of having a lot of devices on the same chip. And then the second popular technology is again based on silicon, but they are called ring resonators. So the top right figure you see. So they are very sensitive because, well, because they are very optimized for a particular wavelength. So you can ideally operate them very fast, like more than 40 gigahertz. But the problem with these ring resonators have been that the resonance only occurs for a specific wavelength. So if a modulator has been made for example, for 1500 nanometer wavelength, it will not work for 1550. And that limits its usability, because a lot of time they also become fabrication sensitive. So with a tiny bit of a mess up in the fab, this resonance shifts. And then another promising technology have been these germanium silicon based modulators. So they have also been shown high speed, like 40 gigahertz, even high modulation efficiencies. But what's bad with them is also the thermal stability. So you cannot operate them in adverse conditions. And also it's hard to make them compatible with the CMOS technologies. But overall, the only technologies which have made it to market is lithium niobate. So you can see here that there is a Thor Labs based lithium niobate modulator. So this one operates only up to 100 megahertz. But the one which have been actually also been shown from research groups, they have been demonstrated very fast, like 100 gigahertz modulators and amazing device performance. But again, the problem with lithium niobate modulators are that they are very bulky. So ideally you need a whole piece of block, and it's impossible to integrate it on a single chip. And also the size of these devices are millimeters in length, so they are too large, and hence also not CMOS compatible. So basically we need an alternate technology. So that's the whole motivation from the slide. And what we are trying to do is, so we are trying to see if we could do the same with graphene. So why graphene? Because, so I don't know how many of you are familiar, but at least, well, some of you have worked on graphene, so probably you know that so it's a very interesting material in terms of electronic and optoelectronic properties. So it has a band structure like this. So it has this Dirac cone. Yeah, so it has this Dirac cone, and it's only touching at the Dirac point. So the speed of the charge carriers is basically given by the slope of this Dirac cone, which is like super sharp. So ideally, you have the charge carriers moving in graphene of 10 to the power 6 meters per second, which is very, very fast compared to any existing known semiconductor. And so this results in the highest mobility known to us compared to any other semiconducting materials we know. So that's a very good advantage. And then graphene also has a very fast response. So the top right curve you see It's just basically plotting the charge carrier decaying with time. So graphene has almost a response time in the order of picosecond. But what's even more interesting is that you can tune the optical properties of graphene based by simple gating. So basically, it's like I can tune my optical absorption in graphene by simply applying a tiny voltage to my device. So optical conductivity model of graphene, it has basically two bigger components. So there are interband transitions, where you basically have you shine light, and the charge carriers they move from the valence band to the conduction band. So this results in change in conductivity. And then there are these intra-band transitions where you have charge carriers hopping from the same band, like from inside the valence band. The ones which are dominating are the interband. And so what happens is the optical absorption in graphene is basically is huge whenever the energy of the whenever the Fermi energy is basically less than half of the photon energy. So so here so let's say we talk about datacom wavelength, which is 1550 nanometer. So for 1550 nanometer, the when you convert it into energy, it's basically zero 0.8 electron volts, and half of the energy would be 0.4 electron volt. So if my Fermi energy is here, which is, let's say, more than minus zero 0.4 electron volt, if I shine light, there would be transitions available, and my graphene is still going to absorb. But once this Fermi energy goes above this 0.4 electron volt, there are no more available states inside the system, and there cannot be more transitions. So the absorption, so graphene doesn't absorb anymore. So this principle is basically called polyblocking. So once graphene reaches polyblocking, there is no absorption. But while the Fermi energy is below half of the photon energy, it can still absorb. So you can see in these plots, the one in the left. So here the absorption of graphene is plotted. So graphene absorbs until it reaches the Fermi energy, which is 0.4 electron volt for a datacom wavelength. And once it crosses the threshold, the absorption drops heavily. So this is how you basically tune the absorption in graphene. And you can see that compared to other technologies, for example, the green curve, which belongs to silicon, so this change is huge. So this has a huge advantage over silicon-based passive devices, for example. And in graphene also, it depends a lot on the quality of graphene. So you could see that here we are talking about so basically, if you increase the mobility of the device, you increase the lifetime of charge carriers, and the transition becomes more and more sharper. So even for a crappy graphene device, which is, let's say, 1,000 mobility, it still is much better than silicon. And not only you can modulate the absorption in graphene, you can also modulate the refractive index. So this is another interesting part. So you could, at the end of the day, you could have both electro-absorption as well as electro-refractive modulation from a simple graphene device, even from a same graphene device, but you can even play around and make it more specific as well. So here you see it as well, that when you crosses this polyblocking regime, basically half of the photon energy, the refractive index changes a lot. Okay, I hope it's clear, because my whole project is based on this. So if you have
Sorry,
any
Hitesh,
questions.
I probably missed the point. Like, how do you set this 0.4 EV for graphene?
Yeah, so you basically change the gate voltage of your device, right?
Yeah.
And based on the dielectric, you can calculate how much, like at what Fermi energy your graphene is there, right?
Yeah.
And that's basically so on this axis when I'm tuning the Fermi energy, you can understand is just by that I'm tuning the gate voltage of my device.
Okay. Okay. So basically, it is tunable thing in graphene.
Yes. So you electrically tune the Fermi energy, and you see basically the effect in optics.
Okay.
Okay.
Sorry, I had a question from your previous slide. Can you please go?
Yeah.
Yeah. So I am new to this idea. So I just want to ask. Let's say, is it always the main goal is to increase the band, increase the modulator frequency of these modulators? Let's say I have a 1 gigahertz modulator and I have a 100 gigahertz modulator.
Yeah.
So which one will be preferred? The 100 gigahertz one?
So the thing is, so bandwidth or frequency is one of the desirable factor. But of course, if you want to have something commercial, you want it to be best in many things, right? So it needs to have lower power consumption. It also needs to have higher modulation efficiency. It needs to be small enough. It needs to be CMOS compatible, and it also needs to be fast. So the current technologies which are already, well, I would say, which are already in the market, they're already 40 gigahertz. So something less
Okay.
than that is hardly going to make to the market. So you need something better than this.
And just one small question. So when the frequency increases, so in these waveguides, the loss also increases, right? At higher
That's
frequencies.
not necessarily true, but I mean, indeed, once at, so every device, it's only operatable up to a certain frequency, and then
Right.
the losses kicks in.
Okay.
So I think you're asking about the frequency response of a device. So basically, it goes like 1/2 pi RC.
Hmm.
So up to F3 dB, up to like 50% of the losses. So the device is considered as workable. But after it reaches this threshold frequency, the losses increases, and you do not want to operate into that frequency regime.
Okay. Okay.
Okay.
Thanks.
Okay. So yeah, basically the main message from this slide was that you tune your graphene device electrically, and you can basically modulate light. Okay. So now what I was specifically working on was a structure called dual layer graphene electro-absorption modulator. So it looks something like this. So you have a waveguide, and so we were working with silicon waveguides, and you basically couple light into the waveguide through an optical fiber, and you also read similarly from the other side, from the back side. And then I have one graphene layer in the bottom, and then another graphene layer in the top. Now you would ask me, okay, but where is your gate to tune this graphene? Now the thing is, there are two graphenes here, and they basically act as a capacitor. So they tune each other. So the top graphene is basically tuned by the bottom one, and the bottom graphene is tuned by the top one. So both of them, when you apply a symmetric gate voltage, they tune each other and they move together towards the higher Fermi energies. So what you should get is something like this. So when you increase the gate bias, at some point it reaches this 0.5 of the photon energy, and the transmission increases of your device, or the absorption decreases like it was in the previous figure. And the same thing happens also in the negative direction. So it should be a symmetric response. Now, some key parameters about a modulator device is basically, so one is modulation efficiency. So that basically gives you an idea of how sharp is this transition, right? Because at the end of the day, you do not want to apply a lot of power in your sample, and power basically depends on how much voltage you apply. So the smaller this voltage require for you to have this transition, the better it is. So for smaller voltage, you will have a very high slope, and it would give a higher modulation efficiency. And then, as we just talked about, the other important parameter is the bandwidth. So it also needs to be very fast. So bandwidth of a device is basically 1 over 2 pi RC. So you need to reduce the resistance and capacitance of your device to increase the bandwidth of your sample. And then another important thing is hysteresis. So here I only show one trace, but ideally you would like to modulate here. So you would like to do a lots of these traces on top of each other. And if there is a huge hysteresis between them, then you will basically never have the same response. So ideally you would like something which doesn't have charge traps or any other leaky mechanism going on, and it follows the same curve every time. And the last thing which nobody else has explored so far is this polyblocking, is basically reaching this saturation regime. So we also wanted to reach here. And why so is because here, as I told you in my previous curve, in my previous slide, that this is the place where absorption is 0. So that means that your graphene is not absorbing anything, and the intrinsic losses from your graphene device is 0. So this is the stage where there are no losses from graphene and it only modulates phase. So this is like a dream place for a phase modulator operation where you only modulate phase without having any intrinsic losses from graphene. Okay. Now, so I'm not the first one who has made this dual gated geometry in modulators. There have been many works earlier, and some of the important ones I'm highlighting here. So there were two in the beginning in the last decade where they managed a decent modulation efficiency, but with a very tiny bandwidth. And recently, last year, from one of our collaborators, they managed to achieve again a decent modulation efficiency with a reasonable enough bandwidth. But they had not much information about hysteresis, and they were very far to reach this polyblocking regime. So now our goal was basically to win in all these aspects. So we wanted a higher modulation efficiency, we wanted higher speed, we want no hysteresis, and we also want to reach polyblocking. So now, to explain you about the modulation efficiency, what we just talked about, that we need something which has a higher modulation efficiency. That means less voltage required to have this transition. And as you know, in a parallel plate capacitor, basically Q equals to CV. So in order to have the same charges, either you increase the capacitance or you increase the voltage. So if you want to decrease the voltage, basically the idea would be to increase the capacitance of your system. But now the problem is bandwidth is 1 over 2 pi RC. So bandwidth goes inversely proportional to capacitance, whereas modulation efficiency goes directly proportional to capacitance. So it's like you have to make a choice here. You cannot increase both the parameters together. So what we did was we decoupled this problem, and so we increased the modulation efficiency of our device by increasing the capacitance of our system. And for bandwidth, we basically tried to find a way around by increasing the mobility of the device. So when you increase the mobility of the device, at the end, you improve the resistance. So you decrease the resistance highly, and it improves the bandwidth. So basically, the idea was to make high-quality graphene devices. And I think many of you already know that boron nitride is basically still the state-of-the-art encapsulant for graphene devices. So this is one example of a graphene device we measured here. So this is done at room temperature. So we had a nice whole mobility of 33,000 in the whole regime. And here I show again basically the modulation performance of this device. So when you increase the gate voltage, you go to this transition when you reach half of the photon energy, and the absorption or the transmission starts changing up. But now you see that in my cases, I do not have traces which are going all the way up to polyblocking. And this is because all my devices, they started to leak before even it could reach polyblocking. So here I plot a leakage current of the same sample with the same gate trace. And you can see that once it reaches this particular threshold voltage, the leakage current starts shooting up. So that basically means that my dielectric is not capable enough to push further more the Fermi energy. So now the goal is basically to find a high K dielectric, which has a strong capacitive coupling so that we can improve the modulation efficiency. And we also want a higher breakdown field, so we could still reach the polyblocking. And unfortunately, boron nitride is not enough. So we started to look around.
Because I had one question.
Yeah.
So what is the typical HBN thickness in your case, in your devices?
So we were using probably 7-8 nanometers, but at the end, breakdown doesn't depend on the thickness.
Yeah.
Right. So it's always so the breakdown field of boron nitride is 7.5 megavolts per centimeter. So of course, if you increase the thickness of your boron nitride, you can apply more voltage, but the effective tuning would be same.
Yeah. So it is related to the electric field. But anyway, I was just trying to understand what is the electric field typically you get for the leakage current to develop, or what is the let's say, voltage corresponding to this 7 nanometer BN? That's rough number.
Yeah. So basically so roughly it is 7.5 megavolts per centimeter. So that's roughly 0.7 volt per nanometer. So you could multiply by, let's say, for a 5 nanometer boron nitride, you can apply up to 3.5 backgate voltage.
So you guys get the same boron nitride where we also get like Tagasi, Taniguchi, and Watanabe?
Yes. So this project was from them, but now we also have another source.
I see. So my point is do you really see that this breaking voltage, breakdown voltage, is really 0.7 volt per nanometer, or it depends from sample to sample?
No, it's so I actually did a detailed study about this. So I made these metal insulator metal capacitors. So basically, I took 2 metal electrodes and I put boron nitride flakes in between them.
Yeah.
And then I intentionally break down each flake, and I actually got something like this. So this is a reasonable number to assume while operating any of your device. So 0.7. Yeah. But what I have noticed is also that for thinner flakes, you could push a little bit more higher.
Oh, for thinner you can push.
Yes. So for thinner, it could be slightly higher, but the error margin is a huge. So it also depends on luck, because you could also have a tiny pinhole in a thinner flake, and you could not do anything.
Yeah. So my intuition is that for thinner it would be like worse because you can have pinholes.
Yes, I mean that's everybody's intuition, and but it's the other way around. So there are a couple of papers I can send it to you later. So they basically did conductive AFM with an AFM tip, and they checked different thicknesses of boron nitride, and they found that for thinner ones, the breakdown is very high, and that's what I also observed in my case study.
I see. Okay, good.
Okay, so yeah, basically the idea was we wanted to look for some dielectric which was high K and also had a higher breakdown field. So here what I plotted was so we know basically the permittivities for each dielectrics we had, and we also know the breakdown fields of them, so we can extract how much Fermi energy we can reach with that breakdown field. And so here basically you could see that with Hafnia, we could reach very high Fermi energy, like more than 1 electron volt, compared to all the other dielectrics. And with boron nitride, I was not even able to cross this polyblocking regime, which is 0.5 electron volt. So naturally, we went with Hafnia. But now the goal was to have a high quality device and better dielectric. So Hafnia would give a better dielectric performance, but Hafnia would also give a very bad quality in terms of graphene performance. So a lot of work which has been done in the past with 2D materials and integrating them with high-K dielectrics. So high-K dielectrics have these lots of charge traps, and which compromises the quality. And this is why everyone is working with boron nitride encapsulation and not other dielectrics. So that's where this 2D, 3D integration comes into picture. So what we did was we basically took a boron nitride stack. So you have 2 boron nitride flakes, and we put Hafnia in between. So now you still have the high K properties coming from the Hafnia, but your graphene, which are these hexagonal lattice, the bottom and top, and none of your graphene sees Hafnia directly. So in this way, you actually maintain the quality of your device because of boron nitride, and you still have high K properties from the Hafnia. So it was not so simple to grow this Hafnia directly on boron nitride. So it took me 2 months to optimize this recipe, but it is doable. So this is also.
Why do you need two HBNs? Like one HBN and one hafnium should work, right?
So one HBN and one hafnia should work for one layer of graphene, but we have 2 graphenes, so we want both of the graphenes to be high quality performing. So yeah, you are right. For single layer, just one is enough. So yeah, basically we improved the hafnia growth on our boron nitride, and you can see that that if you just barely try to grow hafnia on a boron nitride flakes, I was growing 10 nanometer hafnia and I was getting 10 nanometer holes. So indeed, it's not so straightforward. So you need to play around with the temperature, your ALD recipe, and also seed layers. So eventually we found that if we use a 2 nanometer seed layer of silicon dioxide, and if we grow everything at high temperature, 250 Celsius, we managed to grow a very nice hafnia, which was almost the roughness of boron nitride. So now you could see that, so here I basically bring back to, again, similar device performance as I showed earlier for boron nitride. So these are actually, so some of them are the same devices, and I think this one is a different one. So all these devices, they were breaking down around 0.4 electron volt without reaching this polyblocking. But when I incorporated hafnia in between, we actually managed to reach more than 0.5 and reach this polyblocking regime. So in one way, we achieved this task here. And for the static characterization, for looking for the modulation efficiency, so here you could see this is another device with hafnia in between. So we did a fit here. So this was the sharpest region in my trace. And we actually found 2.2 dBs per volt, which is much higher than any of the works which have been done before. So also, this is just a picture of how a device looks like on my chip. So here, like, this is one waveguide. So at the end, you have these grating couplers where you actually poke an optical fiber and you try to couple light. And then you see these 2 metal pads. So you drop one stack before you make one bottom graphene. You make electrode to it, and then we grow hafnia over all of it. And then we put a top stack and put the second electrode. And that's how we get a capacitor there. And then again, this is the silicon waveguide, and you have another grating coupler in the end where you again come with an optical fiber to read out the signal. And another important thing to to show here was the hysteresis. So here there are two traces, the green and the blue, and you can see that, well, they do not completely overlap over each other, but they are still much, much better than what has been done before. So we are moving towards a low hysteresis regime with this boron nitride encapsulation. And you could see a stark difference when I have only one boron nitride. So this was a similar device, but instead of having boron nitride, hafnia, and boron nitride, I had only HBN and hafnia. And you could see that the traces, they don't even overlap, and they have this huge offset because of charge traps. So indeed, this double encapsulation helps a lot to reduce the hysteresis. Okay. And now we also wanted to check the speed of our devices. So for this, so this is how a block diagram of my setup looks like. So what you take is you take a high-speed vector network analyzer. You send a high-speed pulse signal, basically an on-off bits like 1, 0. And this bits, so you basically have a high-frequency modulating electrical signal. And then you couple this with a bias T. So with a bias T, so now you could couple with a DC source voltage. So you could, let's say, you send 10 volts here, and then the high frequency signal is, so now with this 10 volt mixture with this bias T, you will be modulating at 10 volt. So you basically go sit here, you apply 10 volt with the DC source meter, and then you modulate here like this. Okay. And then this modulating signal, it goes to your device, and here you modulate the gate voltage of your modulator, which in turn modulates the absorption in graphene, and hence the transmission in the waveguide will be modulated. Okay. And then you read this with the photodetector. And if you read it at the same clock frequency at which the signal was sent, then you can actually see how much, basically if you're getting the same signal or not. So for lower frequencies, you do receive the same signal back. But once you start increasing the frequency more and more, there are more losses in your system, and the response drops down. And ideally, so this frequency bandwidth is basically goes over 1 by 2 pi RC. And so around 40 gigahertz, we noticed that we had 50% drop in our device performance. So this is called the F3dB bandwidth. And compared to what I showed you earlier, so this is again 10 gigahertz improvement from the previous measurements. And then again, another important thing to look for high frequency measurements is to plot an eye diagram. So what you do in this case is you have a pulsed signal, which is 1 and 0 bits. So these are random, it's a random signal with 1 and 0. And the goal is to plot that this ideal signal goes through your device, and then you plot it on top of each other again and again. So 1 bit would goes on top and the 0 goes on bottom. So ideally your eye diagram should actually look like a square, but eventually it looks like an eye because there is a rise time and then there is a fall time of the signal. And in a colloquial way, you could say that the more wider your eye is, the better your signal is. So you could see that when we plotted our device performance at 28 gigabits per second, we had a very nice open eye, whereas it looks like it's starting to close at 40 gigabits. But nevertheless, we still have an open eye diagram at 40 gigabits, which is quite remarkable. And yeah, this brings me to the same state-of-the-art slide which I showed you earlier, compared to all the dual-gated electro-absorption modulators on graphene. So we improved in all the parameters we were looking forward to. We improved the modulation efficiency, the bandwidth. Also, we have nearly hysteresis-free data, and we also managed to reach polyblocking. So yeah, I mean, just to remind again, so this polyblocking is very interesting for future experiment. For example, if you want to make an efficient phase modulator, then ideally you do not want to have changes in your absorption and just modulate phase and without any losses. Okay, so yeah, so this is basically my last slide. So I wish I could say that all this I did myself, but no. Um, uh, so this was an incredible effort from lots of people. So some of the major ones I've highlighted here. So I worked mostly with the postdoc here, Barnard Terrace. So I basically learned everything from him. And we had some theoretical support about simulations from a master student, Lorenzo, and of course, Frank. And so all the high frequency measurements, I was measuring them in CNIT. So it's a telecommunication laboratory in Italy, in Pisa. And the silicon waveguides and all the substrates, we got it from IMEC. So yeah, with that, thank you. If you have any questions, yeah, ask me.
So it is your devices are made of exfoliated graphene, right?
Yes, so far all the devices are made on exfoliated graphene, what I showed here, but there are also like works from our collaborators, which have shown them with single crystalline grown CVD graphenes. Because I don't know if you remember, so the first picture I showed about these like transition with different qualities of graphene. So even with the crappy graphene, you can have a very nice change in absorption, much better than silicon. So
I see.
So even with CVD, people have reached very nice speeds, like 40 gigahertz and so.
So then, what is the challenge? Let's say, why are we not shifting from silicon to graphene right away?
Well, they are moving forward. So the collaborators I showed in CNIT, they have now a spearhead project in Graphene Flagship, and they are eventually trying to make it into a company. And their goal is to make graphene modulators, basically, for commercial applications. So there is a movement, I would say, but still, I mean, so far all this has been only demonstrated in labs, right? I mean, even with CVD flakes, so they are not done with polycrystalline film, which goes everywhere, right? So these are single crystalline flakes, so they are much higher in quality, but they are also crystals, so you need to align them, and there still needs some human touch, I would say, in fabrication.
I see.
Just to interrupt, hi Hitesh, I hope you are well. I'm Surajit here. So
Yeah, how are you?
yeah, just to point it out a little bit in the case of the silicon industry overwhelmed or the graphene has take place that point. So how much the point is my point is how much is scalable. Like your device is too much complicated structure is so far, but is it like on a single integrated chip which is can be a industrial take place? As you mentioned also the CVD in that case, but my question is how it is a scalable.
Yeah, so good thing about graphene is that it could be easily integrated to any silicon passive structure, right? So you could use existing state-of-the-art silicon passive waveguides and just use graphene on top. So that's what we demonstrated here with exfoliated flakes, and my collaborators have done with CVD. So at the end, it is scalable. So you could do the same with CVD graphene,
Sorry, and one more thing is that how much is reproducibility? I have seen a lot of thing in the fundamental science. I'm sorry to that. Many graphene experimentalists is here, but the reproducibility is not that level. I have heard many talks, but so how much is the reproducibility here?
So the devices I made, they were very challenging, right? Because I was putting two stacks with exfoliated flakes, and
yes,
I was also growing Hafnium between them. So even for research, this was a lot of work and very challenging. So I would say here the reproducibility is not so high, but the similar experiments have been done with CVD, and there people have shown consistent performances, and they are quite reproducible. But so of course they are not the same performance like what I showed in my device, because this is done with exfoliated and they are done with CVD. But nevertheless, they are much better than silicon. So it is yeah, it is a way forward, I would say.
Nice, thanks. Nice talk.
Yep. Yep. The thing is, we never looked very close to that step. And like my boron nitride they were thin enough, so they were all less than 10 nanometers. So we also did not notice it. But even if there is a step, it doesn't matter, because what's important is to have Hafnia between these two boron nitrides. And so even if it breaks at this step, it's actually, we don't care.
Sorry, I have one more question about that. You have mentioned that Pauli blockage. So can you explain a little bit more? I have little bit of doubt around it. So I am going above the Fermi levels, means about the Dirac point, above more and more and more. Why should not I go? Means where is the states are there is no available state?
Yeah, so in graphene, basically the optical absorption is dominated by interband transitions, right? So you shine light, the charge carriers basically goes from the valence band to the conduction band. Okay.
Yeah.
But now the thing is, so these transitions only happen when your Fermi energy is less than half of the energy of a photon. So basically, less than h bar omega by 2, which is 0.4 electron volt for a 1550 datacom wavelength. Okay. But once your Fermi energies goes above this h bar omega by 2, there are no more available states for transition to happen. And then graphene doesn't absorb anymore. So you reaches in a complete zero absorption state, which is a polyblocking.
So above, let's say above plus h cross by omega by 2, above that, there is a gap, band gap?
Now there is no band gap. It's just there are no empty states available in your.
Okay, no empty state.
Yes.
I see.
So sorry, can you repeat your question? No, I mean, so the reason to improve hysteresis is basically boron nitride encapsulation, right? I mean, the same what you do with your devices. So once you put boron nitride, you have very less charge traps, and that improves. Yes. Sorry, can you repeat your last sentence again? I didn't hear. Yeah. Yeah, yeah. Of course. Yeah. So these devices I showed, I mean, they are really pristine devices. So there are ideally no bubbles in your stack, and they are extremely clean. So you do not want bubble interfaces in your device. I mean, not only it gives these charge traps, but it also gives a non-uniform in homogeneity, and that basically results in different dopings and different gating performances. So you do not want that. Yes, all these devices are at room temperature. So the thing is, these devices they are made um, ideally for commercial applications or to show their worth to go into the market. So you do not want anything which is cold. You want everything at room temperature. So this transition, the polyblocking transition I showed, instead of being a slope, it would be very sharp at low temperature. And yeah, it would be very nice, but it's it's not commercially viable. Yeah. So so I don't know how many of you have faced this personally, but so what was my impression was, for example, when I was in BITS, so I was working with two professors who are very active in research, and they even have some small facilities to measure some samples there, but they were struggling a lot to collaborate with someone to give them some samples. And not only them, I saw that it's like a common trend in India, or any place, even here, I would say, especially for small research institutes, they struggle a lot to collaborate or to find the right resources for to basically to have samples for them, because it's not viable for them to have their own clean room, because in terms of fabrication, the most cost is not only buying equipments, but actually the majority of the cost is maintaining a clean room. And you need to maintain clean room, you need to make sure everything is running, you need to hire PhD students, you need to train them, you need to have the correct know-how, and there are like lots of tiny costs which eventually adds up, and it's not worth doing it yourself. So it's fine, for example, doing it in TIFR or ICFO, where you have big facilities, to do it everything ourselves. But I was just thinking in terms of for small research places, if it would be helpful for them if there was a place which could sell them simple fabricated samples. So, for example, pre-patterned electrodes, pre-patterned markers, like simple thin film deposition, high resolution nanostructures. So these could be used for plasmonics project, metamaterials. So any chemist, solution processing guy, they could just use electrodes and spin coat something on top and measure devices electrically. So things like these, very simple things. So basically, my idea was to look around and do this survey and see if there is a demand or if there is an actual need um, from people. So so yeah, that's what I'm doing right now. So I prepared this small survey and I'm sending around everyone. Yeah. So yeah, it would be nice if any of you can also fill this survey. Well, basically anyone who does a fab. So maybe I can send it to Subhajit later and he can circulate around. And it would be even super helpful if you could ask some of your friends, or like your professors, or even professors in your old colleges who doesn't have proper resources but are still interested in research. So basically those are the actual people who need help. So this is the only way we could make research accessible to all. So yeah.
So basically, you are planning to like establish some foundation to do this, like some business model or something like that.
Yeah, so I'm not planning to do it yet, but so right now I was just looking for the need. But yeah, I mean, ideally, if there is enough need, I don't think it's a bad idea to set up a
Yeah,
small academic foundry, for example. Um, and especially like very simple things, they could be standardized, and would be very nice if we could make them itself in India. And even tiny places like which nobody has heard of, they could start doing some meaningful
yeah,
research. So
yeah. Definitely, nanoelectronics. One of the bottleneck is that like
yes,
we need, yeah, good idea.
yeah, I
But
mean,
you
so
need lots of funding, initial funding as well, right?
you would need initial funding, true, but the thing is, so so what I was thinking was, like when you ask, for example, a professor from BITS if they can make their own clean room, train PhDs, they would say, okay, we don't have enough funds. But if you just give them an option that you can buy one sample, they would probably have money to buy it, right?
Yeah,
So in this way, I was thinking that this might still work. And yeah, for initial funding, you do not need to start something big, right? All you need is a tiny evaporator, one photolithography, and a homemade reactive ion chamber, and you're good to go. Um,
yeah, yeah.
so yeah, yeah. I don't know if any of you have any questions or any interest in this regard. Yeah, please get in touch with me. I mean, if I do something, yeah, I would keep you involved.
Yeah, just to one point, you are right that always in this kind of a small institute, rather than, as you mentioned on in your talk also, like what part you focused, as you mentioned that you don't want to show the low temperature part. Actually, the writing the project and getting funding, always this kind of a strategy always good. In our India, people are always facing that how to write a project so that you can grab a funding. So this is also involving every places, even including our low temperature business and all. So once you said in your project that okay, I got a result like in a 4.2K or like a millikelvin range, maximum who are the funding project said that what is the use of it. So you know that until and unless you have shown some applied kind of a thing, nowadays it is very hard to get.
Yeah, sorry. So you are asking what is the application of this setting up a foundry, or
No, no. I am saying that why this funding has a problem.
well, I mean, I'm too young to answer that. I have no idea.
No, no. I am just give you the one point that's create one problem.
Yeah, I mean the problem is in India. What I see is that you need to. I mean, so far everyone is doing only fundamentals, right? And there are very less people in doing applied stuff.
Yeah, that's I give
Now,
you the one point. You showed that you don't want to see the low temperature part. That is the one strategy. That is in kind of a thing.
so the thing is, indeed, I mean, so as such, graphene has been studied at low temperature, right?
Yeah,
So even if I find something very sharp, it's not going to be something remarkable to the science
exactly.
community
Yeah.
for me. I mean, it has already been shown, but maybe with this new architecture, I could show something even better and maybe get a
Hmm.
small paper out of it. But that's not the goal, and especially this project, this was done in collaboration with Graphene Flagship. So I mean, Frank is one of the leader of optoelectronics work package of Flagship, and this project was only aimed to go in the direction in which Flagship is going. So for this project, the goal was indeed to just show things at room temperature. So this was a highly directed only towards applied. So like you said, I mean, this is, yeah, you could say that this is a funding strategy, but yeah, so it's like very focused according to Flagship direction.
Exactly. That is one has to be put in every foundation wherever you currently do. Like I tell you the one thing, like say the sensor, you want to make a sensor. whatever be the sensor, like if you show that low temperature performance, nobody will like to fund you.
Yeah. Yeah, I mean, especially when you are looking for commercial, like industrial partners to fund something, you cannot show them low temperature performances. I mean, um, so they want to invest in something which can go to market in the next 10 years and not. Um,
Exactly.
so I mean, yeah, this is one direction like which I think we should also move forward in. Like we should look for more applied things and try to bring industry back in India, right? Because so
Exactly.
far there are very few people who are doing applied things there. And I mean, take an example of the IFR. I mean, it is one of the best places I know who does research, but 95% of people are only doing fundamentals.
Yes, if you want to survive that fundamental science, now there you have to be at least 40% towards applied, because what I have heard currently many direction that government just fade up, I guess. I don't know what is the government strategy, but this kind of thing is happening.
Yeah, so I mean, it's also good to look into applied projects from my perspective. I mean, it brings industries, homes, and yeah, it's the future way forward. Yeah, 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 yeah. Thanks a lot for inviting me. Great catching up.
Yeah, yeah. Thank you, Hitesh.
Yeah, thanks. Okay, bye bye.